Hello everyone, welcome back to mychemcorner. So before we move into the video, if you are new here, welcome to my channel and don't forget to subscribe to the channel and hit the bell icon for further notification. So in today's video, we're going to talk about closed pack structures. So we're looking at the type of the arrangements in different dimensions of these atoms. So let's see one by one. Now here, due to stronger intermolecular attractions in solids, the constituent particles are closely packed in three different dimensions. So we all know the characteristic features of solids, that all these atoms are closely packed, their intermolecular attractions are very strong, they are not compressible and all of that. So because of all these features, they form a very close packed structures in three different dimensions. So here we will be learning in detail regarding these close packed structures in 1 dimension, 2 dimension and 3 dimension. So before we move into this entire video, I would like to say that when you are learning about close packed structures, all that you need is a lot of imagination regarding how these atoms are placed. If you're good at diagrams, then it would be nice if you could draw a diagram. But otherwise, a lot of imagination about how these atoms are going to be placed in a 2 and a 3 dimension. 1 dimension, yes, can be drawn on a paper. It's easier to identify, it's easier to understand. But when you move into 2 or 3 dimension, you're moving into other axes when you're looking at it. So there, a lot of imagination is required when you're trying to understand close packed structures in 2 and 3 dimensions. That's why I told imagination of how these atoms are going to be arranged would be helpful. Or if you want to know an easy way of learning 2 or 3 dimension, you can use bangles. Probably you have your mom's bangles, your sister's bangles, or any. You can use those bangles, try to arrange them on the floor or on a book, and then try to understand how the close packed structures on a 2 or 3 dimension works out. So let's move into each one in detail. We'll move into the close packing in 1 dimension. Now what do you mean by 1 dimension? It's just along, all the atoms are placed only on one particular axis. So here I have a diagram. Now here if you see, the atoms are placed in a row, just in a row, along one of the axes. So here if you see, the spheres are arranged in a row touching one another. They are in contact with one another. That's why we say solids are closely packed. Now each sphere is in contact with 2 of its neighbors. So here if you see, I'm taking the second atom. Which are these other atoms that it's in contact with? The first atom and the third atom. If I'm taking the third atom, it is in contact with the second and the fourth one. If I'm taking the fourth atom, it is in contact with the third and the fifth one. So in this case, if you see, each sphere is in contact with 2 of its neighboring atoms. So when we say that it is in contact with 2 other neighboring atoms, there is a particular terminology for it. It's called as coordination number. Coordination number meaning how many spheres are in contact with that particular sphere, or how many spheres are touching that particular sphere. So the coordination number of this particular atom is 2 because it's contacting 2 atoms. The coordination number of this particular atom is also 2 because it is touching 2 atoms. So in a 1 dimension close packing, the coordination number of any particle is going to be 2. So here 1 dimension is easier because you just need to learn how these atoms are closely packed only in a single axis. Now let's move into the next one, which is close packing in 2 dimension. So here now you need some imagination, right? When we were small or when we were kids, when we had when we had a lot of balls, what did we do with those? We tried to arrange them in a single row and then we tried to place them one above the other. That's exactly the same imagination that you're going to have even now. So here for 2 dimension, what are you going to do? To the existing 1 dimension, I am going to place rows above each other. So here I have 1 dimension. So this one dimension, what are the different ways in which I can actually arrange rows above this? There are different ways. Either I can place right above each sphere, or I can place in the depression of each of these spheres. So I have two different ways in which I can actually place my row number 2. So here for my clarification, I am going to name this first row as row number A. And now when I'm trying to place the second row, I'm going to place the second row exactly above the spheres of the first row. So here if you see both the rows are the same, so I'm going to name this also as A because both the rows arrangement are the same. Similarly, I'm going to keep arranging them the same way above. So what happens? I'm going to get the same arrangement in the third and the fourth layer and so on. So here each row in this type of an arrangement is A type because they're all placed in the same arrangement. They're all placed one above the other. So this type of an arrangement in a two-dimensional way is called as A type of arrangement. Now, say for example, can you all see a box here? Right? What was this box all about? I connected the centers of these 4 spheres. This particular sphere, center. This particular sphere, center. This sphere, the center. And this sphere, center. When I connected the centers of these spheres, what was the geometrical shape that I got? I got a square. Therefore, this type of a packing is called as square close packing. So the A type of arrangement is called as a square close packing because when the centers of these spheres were connected, they gave a geometrical shape of a square. Now, if you look at the coordination number of any sphere in this particular type of an arrangement. So in this, if I'm taking for example this particular sphere that is marked on the screen, this sphere, how many other spheres is it in contact with? This sphere is in contact with one above it, one on the right, one on the left, and one below. So totally how many atoms are that sphere in contact with? With 4 other neighboring atoms. So therefore, the coordination number of each sphere in this type of an arrangement is 4. Because any sphere that you take, it is touching 4 other spheres. So this is one type of an arrangement where you get a square close packing whose coordination number is 4. Now this is the type of arrangement where you get similar layers. Now I have another type of an arrangement. So I'm taking the same one dimension. Instead of placing my second layer one above the other of each of these spheres, I'm going to place them in the depression of these spheres. This is called the depression of a sphere. So I'm going to place it in the depression of the sphere like this. So now if you see, are the arrangement of layer 1 equal to layer 2? No, they are not the same. So what happens here? I'm going to name the second layer as B. The first layer is named as A. The second one is placed in the depression of the first layer, giving me an entirely different arrangement of the spheres. Therefore, that layer is named as B. Now what I'm going to do is when I place another layer on B, I'm going to place in the depression of the second layer itself. When I do that, I'm going to get this arrangement. Now when I compare the third layer with the first layer, their arrangements are the same. So that layer is going to be named as the same as first layer. Now on the third layer, when I place another layer in the depression of it, it's going to give me a layer similar to the second layer here. So here I'm going to name this as B because it is similar to the second layer. So here what type of an arrangement am I getting? I'm getting AB type arrangement. Now in this case, I'm going to connect the centers of the sphere. right? When I'm going to connect the centers of the sphere, here I'm getting a hexagonal shape. I'm getting a hexagonal shape. So therefore, this type of an arrangement is called as hexagonal close packing. Now here, when you look at the center sphere, how many other atoms are the center sphere touching? 1, 2, 3, 4, 5 and 6. It is touching 6 other atoms, therefore the coordination number is 6. So for an AB type of arrangement, the type of close packing is hexagonal close packing, and each sphere is in contact with 6 other spheres. Therefore, the coordination number is 6. So here from a 1 dimension, when we come to 2 dimension, we have 2 different arrangement. One is when we place the second layer or the third layer right above the spheres of the first layer, then you get an AAA type arrangement whose packing is a square close packing and coordination number is 4. Whereas in the second type, when over the 1 dimension layer, when we place the second layer in the depression of the first layer, we get an AB type arrangement. In this case, the type of close packing is a hexagonal close packing whose coordination number of each sphere is 6. So now that we know what type of arrangements you get when you try to find the 2 dimension from a 1 dimension, we need to know what these gaps are. If you look at the type of a gap in a square close packing, it is different and much bigger when compared to the gap in a hexagonal close packing. So what is that space between the particle called as? The space between these particles are called as a void. Now this particular space is less in a hexagonal close packing, therefore close packing is more efficient in hexagonal type. What do you mean by more efficient? When we have a solid, when we say that these are closely packed and tightly packed, we need to say that the space between these atoms should be very less. That's when we say it is closely packed or tightly packed. So between the square close packing and the hexagonal close packing, which one has lesser space in between the particle? The hexagonal close packing. So that means close packing is more efficient in a hexagonal when compared to square close packing. Alright, so now we know how to find out the 2-dimensional close packing from a 1 dimension. Let's move into the next one, which is close packing in a 3 dimension. Now here we need a lot of imagination. Of course, I will be showing you the diagram, the model and all of that, but you need to have a lot of imagination so that you can understand how this entire concept of 3 dimension works. Now for a 3-dimension close packing, the 2-dimensional layers are placed one above the other. So say for example, I'm going to take my 2 dimension that I just learnt and I'm going to stack them one above the other. There are again 2 different ways. One is I can place one above the other, keeping the spheres right above the other. In the other one, what I can do, I can place in the depression, just like how we learnt a 2 dimension. Same way we are going to do here also. So here the first thing is conversion of a 2-dimensional square close packing into a 3-dimensional square close packing. So what do you mean by square close packing? The very first thing that we learnt under 2 dimension, AAA type of arrangement. So here let's take I've just taken a 2-dimensional square close packing and then I've just tilted the entire thing. So if I take if I take an arrangement that's physically present in front of me and if I just kind of slant it, this is the type of arrangement I will get, right? If I just push it from here and if I try to make it straight, it will be a proper square close packing. So I've just slanted it to show you all a 3-dimensional shape, so it's easy to understand. Now here what I'm going to do is I am going to place the second square close packing right above the first layer. So if you have not seen it, I will show it to you all once again. This is the first layer. When I place my second layer, I'm going to place right above the sphere of the first layer. You all can notice over here in the very first line. So if you see here, this is the second layer, and that second layer sphere is standing right above the first layer. Now so on, when I keep doing it, what is happening in this case? In all the three layers that went above in the three-dimensional shape, these are standing one above the other, but they are in a three-dimension. So here, the type of arrangement again in this case is AAA type, and this type of an arrangement will give a simple cube. This is the type of arrangement that you see in a simple cube. Alright, now if you connect the centers of each of these spheres, it is going to form a simple cube. That's why we say this type of an arrangement is seen in a simple cubic lattice, and the unit cell, one unit cell of this entire diagram is a primitive unit cell. Now let's move into the second type of arrangement, which is conversion of a two-dimensional hexagonal close packing into three-dimensional. So now from the two-dimension, we're taking the second type of arrangement, which is the ABAB type. So let's see how to do that. So in this, the first thing is you're going to place a second layer over the first layer of a hexagonal close packing. Now, hexagonal close packing from a two-dimension is the ABAB type of arrangement, the second arrangement that we saw. Now, when we take like that and we're going to place the layers one above the other, there are ways in which I can arrange them. So, let's see the first type. So, this is the ABAB type of arrangement. That's a second dimension. Now, if you see, I'm going to place the second layer in such a way it is covering the void. Some places the voids are covered, some places the voids are still visible. So that way when I cover it, I'm going to get different type of an arrangement. Now here, when I see this diagram like this, there are two different ways in which the atoms are placed. At some places you can see that the void of the first layer is covered with the sphere of the second layer. Now that is what is shown here. So this type of a void is called as a tetrahedral void. So when you try to connect the centers of the spheres, you will end up getting a tetrahedron. That's why the void there is called as a tetrahedral void or tetrahedral hole. But some places like here, these places, the void is clearly visible because there is no sphere covering it. Now, in such kind of places, it is called as an octahedral void, and when you join the centers of all the spheres in this type of an arrangement, you will get an octahedron. So that's why it is called as octahedral void. So now if you're looking at the total number of octahedral and tetrahedral void, if say in the entire close packing I have n spheres, we don't know the exact number, so we're just calling it as n spheres. So if n spheres are there in the close packing, then the total number of tetrahedral void will be 2n, double the number, and the number of octahedral void will be only n. So if you have n spheres, then number of octahedral void will be the same as the spheres count, but tetrahedral void will be 2 times the number. So this is regarding placing the two-dimensional hexagonal close packing one above the other in a way where it is closing the tetrahedral hole and the octahedral hole is still visible. Now what we are going to do is, in the second type of an arrangement, what we are going to do here is we are going to place a third layer. The problem is in the third layer. Are we going to place the third layer exactly in the type where the first layer is arranged, or we can have a totally new arrangement? So let's see that. So here when I place the third layer over the second layer, there are two possible arrangements. So this is the same arrangement we just saw in the previous slide, where some of the octahedral voids are visible, tetrahedral void here is covered. Now when I place the third layer above this, it can be same as the first layer, which is the yellow layer. That means I'm going to cover the tetrahedral void this way. So I'll go back and I'll show you what I did. I'm going to place the third layer. When I place the third layer, what is happening? The yellow spheres are not visible, which means they are placed right above the positions of the yellow sphere. So now when I try to tell the arrangement, the first layer and the third layer is the same. So here, when I try to cover the tetrahedral void, AB type of arrangement is observed, which means the arrangement of the A layer is equal to the third layer. So now, the next type is where I'm going to cover the octahedral void. So let me take the same previous slide diagram. Now when I'm placing this, the void that was visible in the two layers, I'm going to place my third layer in such a way this void is now getting covered. In the AB type, that void was still visible. But here that octahedral void is going to be covered. So I place the spheres, the third layer in that way. Now when I placed it, what happened? I can still see the yellow layer. Nowhere the yellow layer is covered. So here I have covered the octahedral layer. In this case, I'm going to get ABC type of arrangement because the first layer, which is the yellow layer, is a different arrangement. The second layer, which is the gray layer, is also a different arrangement. On top of that, the red layer that I put is also a different arrangement because all three layers are visible to me. So it is ABC type of an arrangement. So when I cover tetrahedral void, it's going to be AB arrangement, which means repeated alternate layers are there. Whereas in octahedral void, when I try to cover, I'm going to get ABC type of arrangement. Now, in this type, when I'm trying to cover the tetrahedral void, the type of arrangement is AB type. Therefore, this type of an close packing is called as a hexagonal close packing because now in these three layers, when I place them in a 3-dimension and try to connect all the centers of the sphere, I will get a hexagon. That's why they're called as hexagonal close packing. Now, in what type of metals are they formed? Metals like magnesium, zinc. These are the type of metals in which a hexagonal 3-dimension close packing is seen. Whereas if I look at ABC type, in this type of a close packing is called as a cubic close packing or a face-centered cubic close packing, FCC. Alright, so here this is found in metals like copper and silver. So here, to understand this particular topic, which is talking about close pack structures in 1 dimension, 2 dimension and 3 dimension, a lot of imaginary diagrams are required for you to understand. So basically, if you can think of, say, if you have the same color ball with y'all, you can imagine how you're going to arrange them in a 1 dimension, then you're going to put them in a 2 dimension like one above the other, and then you're going to stack it up as a 3 dimension. But how many different ways can you stack them up? So that way it makes it easier for you to understand a closed pack structures. So here, if you've understood this video, this will help you understand the different type of arrangements of spheres in a solid. So kindly go through this video in detail. If you have not understood, please go through it repeatedly so you understand the entire detail about it. If you have any further inquiries, please don't forget to drop an email in the description box below. Also, if you can have any suggestions, please don't forget to put it in the comment box. I'll see you in the next video. Stay tuned. Thank you so much.